Good afternoon, engineers. Or morning, evening, whatever the time may be, but there is never a bad time to build a circuit. And today we are going to build a very useful circuit, a variable square wave frequency generator, here on Blueprint. At one point or another, every electrical hobbyist is going to need to set a frequency. This could be very low or very high depending on the application. And having a one-size-fits-all frequency generator will be essential to have sitting around, especially since 555 timer ICs are so inexpensive. It is this IC that made America great, the first time. By the way, when I say IC, that's just an acronym for Integrated Circuit. P.S. I hate acronyms. Oh, wait a minute. The 555 datasheet gives us plenty of useful information about the 555 timer, including data tables and schematics for several different designs. As you can see, it's a pretty light read. The schematic that we're going to look at is that of an astable oscillator. Start by attaching a timer to a blank PCB or a breadboard. Rather than soldering the chip on directly, we can solder a socket so that we can interchange the 555 timer without desoldering. The half-moon notch indicates the direction of the IC. If the notch is on the left, that means that the lower left pin is pin 1 and the upper left pin is pin 8. The set frequency, which can be from microseconds to hours, is determined by two resistors and a capacitor. Right next to the astable timing schematic in the datasheet should be equations that dictate the period and frequency of the circuit. Remember that the frequency is 1 over the wave period. 1 period is the time spent on plus the time spent off. Resistor 1 is going to change the duty cycle, aka the percentage of time spent high instead of low. To keep the duty cycle close to 1/2 of the period, this value should be very low. R1 connects pins 8 and 7, and R2 connects pins 7 and 6. As I showed in the schematic, in order to make it variable, I'm going to be replacing the second resistor with a potentiometer. A potentiometer is simply a variable resistor. Potentiometers are probably going to be the hardest thing to find. I was happy to find the ones that I could. I mean, they're not at all common. You definitely can't find them in just about everything. So, you know, take what you can get. The cap goes between pin 6 and ground. As I showed in the schematic, I want to be able to switch between two capacitors, one small cap for the higher frequencies and a larger one for the lower frequencies. This is because the frequency at which the circuit oscillates is directly contingent on how long it takes to charge the capacitor. Hi, I'm from the future. Now I've already completed the circuit by this point, but I wanted to show you what role the capacitor has in setting frequency. The yellow wave is looking at the voltage on the output of the 555 timer, and the pink wave is looking at the voltage on the capacitor. As you can see, they are not only in phase with each other, but also have the exact same frequency. The role that the resistors play is in charging the capacitor. If I increase the resistance, it takes the capacitors longer to charge. And if I decrease the resistance, the capacitors will charge quicker. Now back to your regularly scheduled programming. The one thing I haven't shown you yet is the values that I chose to use. This depends on what range you would like to have. To find my values, I set up two equations and solved for values that would give me around 1 and 20,000 Hz, the audible range. I averaged my answers to settle on a potentiometer value. Here are all of my values. Alright, the time has come to fire it up. I'm going to be powering it from my lab power supply. Why is nothing happening? Oh, right. Yes, you must remember to turn on your power supply. Now I think I killed it. I'll have to double check to be sure. Yeah. Don't be an idiot. Make sure that your lab power supply is not at its maximum value the moment that you turn it on. Otherwise, your 555 timer will explode. If we take a look at the 555 datasheet, we see that the input voltage is anywhere between 5 and 18 volts. This is something that you should keep in mind. It's for this reason that I added a 9 volt linear voltage regulator into the input, as you can see here in the schematic. Like I did for the input, I want to add some connectors for the output too. In addition to having a connector for the output of the 555 timer, which by the way can only sink about 225 milliamps, which isn't nearly enough for most of my applications, I want to have another connector where the 555 gates a MOSFET so I can draw a much larger power. While I do that, please enjoy traveling to the future of this video. There, it's a little while later, and I have added these two terminals. This one here goes directly to the output of the 555 timer, which means I can power things directly from it. The other one is just a switch going through a MOSFET, which I can turn on and off, which means that other things are going to need to have their own power source, and this will just turn it on and off at whatever the frequency of the 555 timer is set to. Oh yeah, and I also added a 9 volt battery connector, so now wherever I am, and for whatever reason, I can set a frequency that I need. Just like that. No. Oh hey! I was wondering when you might show up. Yeah, sorry about that. I accidentally snapped you way too far into the future. Anyway, don't worry about it. I'll send you back right away. Oh good. You're back. Where'd you go? I was just about to demo my product for you. So to show you that it does really work, I've attached an LED on the output. This is using the large capacitor so that it blinks slowly. Now anyway, as you can see here on the oscilloscope, it is matching exactly the voltage on the LED. And if I turn the potentiometer to the maximum resistance, all of a sudden, the rate at which it blinks is extremely slow. But if I go in the other direction, now my frequency is so fast the LED just looks like it's on all the time. Let's zoom in on this waveform. You see, the reason I can't get super high frequencies while using a large capacitor like this is the following. Remember that equation earlier that told us the period that is spent high and the period that spends low? Well, only the period high depends on R1, which means if I bring the potentiometer down to 0, it will theoretically spend all of its time high and none of its time low, which we can almost see right here on the oscilloscope. That's why I included the smaller capacitor, so if I go ahead and flip the switch, and bring the potentiometer up to some value, now you can see I have a frequency in the much higher frequency domain of about 10 kilohertz. Of course, you're not going to be able to see any of this on the LED. However, you could hear it on a speaker. Can you hear it? It might be too high of pitch for the camera. Let me try bringing the frequency down a bit. And it's not super loud, is it? I'll tell you what, I'll just dub the audio over it. Here's what it actually sounds like. Cool, huh? Cool. Now I'll never need to build another 555 timing circuit ever again. Take that, 555 data sheet! Yeah! I'll let the custodians get that.